Welcome to my introduction to pressure control ventilation. My name is Alan Prost, and this is part of the course AMPH 221. In this short video, we're going to explore using a test lung model the effects of resistance and compliance during pressure control ventilation. So let's see what that looks like. Now, hopefully you've watched the other videos looking at volume ventilation so that the test lung model will be familiar to you. This time though, instead of putting in a set volume of ventilation, we're going to actually use pressure control, where we establish a pressure gradient. We're still going to be pushing air across from the mouth into the test lung itself, which mimics the lungs of our patient. We can vary the compliance from high to low in our model. Okay, so this is very similar to the volume ventilation, but you'll notice that this part here looks different, because what we're going to do now is we're actually going to put a weight on here. We're going to use pressure control ventilation. Initially, before we start giving a breath, the ventilator's waiting here. There's nothing going on, there's no flow, so there's no effects of resistance. So P1, our mouth pressures, and P2, our alveolar pressures, are equal. Nothing's occurring at this time. If we look at our graphs, P1 is 0, P2 is also 0. They're both in stagnation until what we do is we're going to establish a pressure control. In pressure, what we do is we basically, just like this graph is showing us, we put a weight or a certain pressure in our circuit, and at this place what we're doing is 25 centimeters of water pressure. When we do that, we're forcing air from the ventilator towards the patient. So our pressure here, our P1, is going to be reading 25, just like the pressure gradient we've established. P2 is going to be a little bit lower initially, because we need a pressure gradient from P1 to P2 to get flow past this resistance. All right. P2 reflects the amount of distension of the spring we have in our test lung. So just like with volume ventilation, except now instead of putting across a certain volume of ventilation, I'm creating a certain pressure on this side of the equation, on the ventilator side. So initially our pressures build up quickly to 25, just the pressure that we've set up in our driving pressure we've set up with our ventilator. Okay, the pressures in the lungs, or the P2, our alveolar pressures, are going to lag behind a little bit, because we need this pressure gradient to drive flow across the resistance. So let's see, as time progresses now, what we see is the pressure in the mouth, P1, has built up quickly to our driving pressure, which was 25 centimeters of water pressure. So P2 will equal the driving pressure of our ventilator. We still need a pressure gradient here to get flow across from the mouth into the lungs. So P2 is lagging behind a little bit. So we can see that P2 here is still below, so we have flow going across our resistance. P2 reflects the amount of distension of that spring, and that spring represents the elastic recoil of our lungs. So the more the spring is distended, the more elastic recoil. As time progresses, what we see is that the pressures in P1 are still now a little bit greater than in P2. We still have a little bit of flow. The flow is declining a little bit, because we're almost got equilibrium between the two. Once P1 equals P2, flow will stop. So right now, the pressures here inside the mouth and the lung are the same, so there's no flow across the resistance. So the effects of resistance are 0. P2 and P1 are equal, and they reflect the distending pressures required to put or to equal this pressure of 25 in both the driving pressure of the ventilator and the lung. So pressures here are in equilibrium, and this is our P plat, just like we looked at before. This is our P plat. All right, so a little bit different than volume ventilation in that our pressures here at the mouth, P1, equal P2. All right, initially these can be a little bit higher, because I do need a flow gradient. I need a pressure gradient to get flow across from my ventilator into the test lung. During exhalation now, we've got the passive recoil of that test lung due to the elastic nature of the lungs themselves, represented here by this spring, forcing the lung from the test lung to back towards the ventilator. Now the ventilator just allows this gas basically to vent into atmosphere, so it just basically goes to 0 atmospheric pressures. But we do require a pressure gradient from P2 towards P1 to get that expiratory flow past the resistance. So initially what you'll see is P1 mouth pressures will drop very quickly to 0, or our PEEP levels. P2, represented by our lung pressures, they'll decline, but it'll take a little bit of time before they finally reach 0, because I need that pressure gradient from P2 from the alveoli across to get flow back to the atmosphere and during exhalation. Now almost all the volume of gas is being pushed right out of the test lung, so P2 is very low and is almost equal to P1. Now all the gas is being right out of the lung, so there's no flow at all. So P2 and P1, our mouth pressures, and our alveolar pressures are back down to 0 because all the volume is out of that test lung. So they're both at an equilibrium. All right? So initially what happened was we put in a volume of pressure in here, and then in our case today was 25 centimeters of water pressure. And that created a pressure gradient forcing air into the lungs. Then during exhalation, we used the passive recoil of the lungs to force the air back, and that's represented graphically. Here was inspiration, then the pressure was held in the circuit. At peak inspiration, there was a little bit of an inspiratory pause, and then we allowed exhalation to occur where the gas flowed from the lungs, represented in blue here, back out to the atmosphere. Okay, so hopefully we've demonstrated a little bit about how the model works. And what I need you to do is to interact with this model a little bit. So we're going to have, once again, you've seen these models of the virtual ventilator. Just going to go into here to full screen view so you can see it all. And what we do in this model is we control things like the driving pressure of the ventilator. Here set at 25, just like in a model. The amount of time that pressure is going to be held on for, how many times per minute, and we can actually have like a PEEP level or a baseline pressure that we keep in the lungs at all the time. So that could be 0 or 5 or even 10 centimeters of water pressure. Again, we can control things like the compliance and resistance of our test lung model, and this gives us some data. It tells us how much volume, this relationship of pressure and the delta P relates to a volume being delivered to our patient. All right. So for our purposes, why don't we set this to 0? All right. And so we'll have our pressure control gradient, our TI, and we can look at the effects of compliance. If we decreased the patient's compliance, so we make it say 20, you'll notice that the pressure here being delivered to the lungs hasn't changed. We didn't change our delta P, but the volume that goes into the lungs drops dramatically. Decreased compliance during the mode of pressure control results in a lower volume delivery. So if I decrease the compliance even more, you'll notice that the volume being delivered gets smaller and smaller. If I increase compliance, making the lungs more distensible, the amount of volume that goes into the lungs becomes greater. So these are the interrelationships we need to look at. Interestingly enough, if I have an inspiratory pause there, oh, sorry about that. If we have an inspiratory pause there, what you'll see in this part of our graph right here, if we have an inspiratory pause, there is almost no effect of resistance. So if I decrease the resistance or I increase the resistance, there's no effect because I have this inspiratory pause occurring. All right. So the effects of resistance in the mode of pressure control are very hard to observe. We'll talk about later on about how you can observe them, but right now you'll notice that there's very little difference between the PIP and P-plat, they're essentially the same at the end of inspiration. So to explore these relationships, I've created these virtual ventilator, the pressure control virtual ventilator that you can utilize. And we'll just click out of that. So you can use the virtual pressure ventilator, and you can work on this worksheet here. So you can look at that relationship between PIP, P-plat, and volume delivery. So what you're going to do, from our initial settings here, you're going to adjust compliance and then set it back to the original settings. You'll increase it, and then you try decreasing it, going back to the original settings, and then place your observations here. All right. Once we've done all these and constructed our model of what happens with increased or decreased compliance, all right, what we'll expect to see with if we have increased compliance, so the lungs are more distensible, for the same pressure gradient here, we're going to notice that, hey, we're going to have an increased tidal volume delivery. With decreased compliance, we'd expect to see a decreased tidal volume delivery. These values will stay the same. We didn't alter the driving pressure of the ventilator. We didn't change any of those things. All we did was alter the compliance of the lung. So let's go back and have you utilize the lung model and determine what happens with the resistance, what happens when you change the pressure control level or the driving pressure of the ventilator. So that's this control here. Okay, so let me just recap. Using our pressure ventilation model, where we adjust the driving pressure of the ventilator that forces air or any medical gas past the resistance into the test lung, what occurs? What are the effects of resistance? What are the effects of altering the compliance or the distensibility of the lung itself? We're going to look at this relationship of forcing a pressure gradient, holding that pressure on the test lung, and see until there's equilibrium between the mouth pressures and the alveolar pressures reflected by P1 and P2. These are your mouth pressures, and these are considered to be your alveolar pressures. All right, or your AL pressures. My name is Alan Prost. I'm your instructor for this course, so if you have any complications or confusions with these, please contact me so we can straighten them out and you can build your model correctly. Thank you very much.